Video will show how to calculate probabilities and find the expected value, variance, and standard deviation of any discrete random variable with a finite number of possible values. The random variable will be called x, the probability is px. So let's define x and just display the results. Notice in this case we have 6 values going from -2 to 3. Any values would have been okay. It's easier if they're increasing. And now we're going to define the probabilities. And this is actually really important. The probabilities have to be non-negative, and they have to add up to 1. If we wanted to display the x and the px together, we could use the r bind function. So notice x corresponds to a probability of 0.2, x equals -2 corresponds to a probability of 0.2, the -1 corresponds to probability 0.1, ... and the 3 corresponds to probability 0.2. These do add up to 1, as you see above. Now, this is actually called the probability mass function for x. So if you list the x values and their probabilities, this is the probability mass function. Having the probability mass function, we can find the probability of any event. So for instance, suppose we wanted the probability of x being between 0 and 2. Now, x equals 0 corresponds to px of 3. X equals 1 corresponds to a px4, and x equals 2 corresponds to px5. So we could find this probability by just taking px3 plus px4 plus px5. That gives us 0.5. We may define something called the expected value of x. And all it is the sum of each value times its probability. In this particular case, these are the actual numbers. Notice -2 times 0.2 plus -1 times 0.1 plus 0 times 0.1 plus 1 times 0.3 plus 2 times 0.1 plus 3 times 0.2. This came out to 0.6. Now, if we've defined x and px as vectors, we can actually calculate expected value pretty easily. And this corresponds to the vectorization of some operations in R. A couple of things. Number one, suppose we have 2 vectors called x and px, and suppose we multiply them together. Watch what happens. Now, if you look carefully, the -0.4 is -2 times 0.2. Each one of these are the product of the corresponding values of x and px. So it did element by element multiplication. But that's exactly what the definition of expected value requires. However, we have to sum these up, and that actually lets us define expected value as just the sum of x times px. In this case, I gave it the name E, and notice the same 0.6 that we got before. A little later on, we'll see what expected value does. Now, for any function of x, we can actually define the expected value of that function of x as just the sum of the f evaluated at x times the probability of x element by element, add them up, just like we have here. So for instance, what if we wanted the expected value of x squared? This fx becomes x squared, and we can actually define this. And now ex2 is 3.4. That's actually the expected value of x squared. On another definition, besides expected value, is something called variance, which measures how spread out data is. The variance of the random variable is the sum of what? First value times the expected value, first value minus the expected value, the whole thing squared, times the probability of x1, plus, and this would be x2 minus the same expected value, the whole thing squared, times px2. And the last one is x6 minus ex squared times px6. Remember, ex has already been defined as a single value by the definition of expected value. We can actually do this computation pretty easily in R, and this can be generalized to any number, not just 6 observations or 6 elements. Look at the variance. What we did is we calculated the expected value. X minus that expected value does element by element subtraction. Square the result. Element by element squaring. This is a vector. This is another vector. This times this, element by element multiplication. That's just the definition of expected value of the x minus ex squared. Sum them up, and this particular expected value is called the variance. The square root of that is called the standard deviation. Now, there is a general result about expected value. And this general result is that the expected value of a linear function of the random variable, let's look at this, is actually the linear function of the expected value. So the expected value of ax plus b is a times the expected value of x plus b. Let's see how this works here. We're going to use the function L of x equals 4x plus 3. So the first thing we're going to do is we're going to define a new function called L of x. And notice this is the definition. So L of 3, for instance, would be 4 times 3 plus 3. Now, I'm going to find the expected value of 4x plus 3. That's just the sum of 4x plus 3 for each x value times the associated probability. Let me call it EY. And I get a number, I get 5.4. But let's take 4 times the original expected value of x, that was 0.6, plus 3. Let's see what you get. Same result. So we could use so if someone said, find the expected value of 4x plus 3, you could have done it just by calculating 4x3 for each x value, taking that, multiplying that by the corresponding probabilities of x and adding them up, or use the theorem. It's 4 times the original expected value plus 3. Let's see how this works with variance. Now, in variance, the general formula is not what you think. As a matter of fact, the variance of ax plus b is not a times the variance of x. It's actually a squared times the variance of x. The b doesn't seem to even appear. Let's see how that would work here with our Lx. We're going to try to calculate the variance of 4x plus 3. Let's see what we get. So here it is with the definition. And we get 48.64. What if we take 4 squared, notice that's the a squared, times the original variance. Original variance was 3.04. Let's see what we get. 48.64. So that theorem is sort of verified in this particular case. For either of them, the standard deviation is the square root of the variance. Now, if you have a probability mass function, you could convert it to a cumulative distribution function by using a built-in R function. It's called CumSum. You'll see what it does in a second. So here's X, here's PX, so this. Now what I'm going to do is I'm going to type CDFX, it corresponds to cumulative distribution function of X. And I'm going to say CumSum of PX. And what CumSum does is, let's actually print it out. Notice the 0.2 is the same as the original PX. Then the 0.3 is the 0.2 plus 0.1. The 0.4 is the 0.2 plus 0.1 plus 0.1. The 0.7, 0.2 plus 0.1 plus 0.1 plus 0.3, etc. The last one is going to add up to 1. This is actually a less than or equal to distribution. Let's look at it. There it is. Now, if you have a cumulative distribution function, sometimes it's pretty easy to do calculations of probabilities. As a matter of fact, a lot easier than working generally with the probability mass function, especially when you have lots of elements or of outcomes in your event. So let's look what we had before. We had this. That was the 0.5. But if you look over here, CDFX of 5 is the probability of everything less than or equal to 5. Now, unfortunately, it includes the 0.2 and the, it includes the 0.2 and the 0.1 for -2 and -1. And actually, I guess it also includes the 0.1 from a 0. But actually, that's part of what we want to include. So what we're going to do here is we're going to take CDFX5. That's the 0.8. We're going to take CDFX2. That corresponds to the 0.3. That's less than 0. And we're going to subtract. And lo and behold, there's the same 0.5 that we got before. This may not seem too useful here, but what if instead of 6 values, you had 600 values? And you wanted to find, for instance, the probability that X is between 100 and 173. In this case, this cumulative distribution function is very, very, very useful. And we're going to work with these in all of the built-in R distributions. One other thing I'd just like to show you, if you have a discrete probability random variable with a finite number of values, you can actually simulate observations from this distribution. And what we use is the sample function. So in this case, SPL is the name of the vector we get. We have the word sample. What this says is sample 1,000 times from the random variable values X and probabilities. The word PROB is very important. PX, and this replace equals true actually lets it basically do the same random observation 1,000 times. If I actually want to look at the first 50 values just so you see what you get, here they are. By the way, humans are horrible at picking random operations. You'll notice here, -1, -1, -1. Humans would never, ever pick 3 negative ones in a row. They'd say, oh, that doesn't look too random. But that's what it is. If we ran this again, we would get different 50 values. In any case, if I wanted to look at the proportion of times that I got different things, I could use the table function. Let's do this right. And notice -2 occurred around 19.2% of the time. The corresponding probability was 0.2. And then we had 0.104, the probability was 0.1. Notice the relative frequencies, which we're calculating here, get closer and closer to the actual probabilities of the individual values. Now, if you want to know what expected value means, let's look at this simulation and actually calculate the sample mean of SPL. And I'm going to calculate the sample variance, which come from the descriptive statistics operations with R. Now let's look. The expected value that we calculated is 0.6. The mean of 1,000 simulations from that distribution is 0.613. Not too bad. The theoretical variance that we calculated is 3.04. The variance of the 1,000 simulated operations is 3.008. So what we get is, as the number of operations gets larger and larger, the mean of the sample gets closer and closer to the expected value of the probability distribution. This is sometimes called the law of large numbers.